The composition of an atom can be represented symbolically as ZXA, as shown here. The symbol X represents the symbol of the element. The superscript A on the left-hand side of X represents the atomic mass number, and the subscript Z on the left-hand side represents the atomic number of the element. As you have learned before, atomic number Z gives the total number of protons present in an atom, while the atomic mass number gives the total number of protons and neutrons present in that atom. Let us work on a simple problem before proceeding further. An atom has 29 electrons and 35 neutrons. Calculate the number of protons and the mass number of the element. Also write the complete symbol for the atom. Since atomic number Z is equal to number of protons, which is also equal to the number of electrons in the atom, we can say that the number of protons is 29. We know that mass number A is equal to the sum of the numbers of protons and neutrons. Hence, the mass number of the given element is equal to 29 plus 35, which is equal to 64. Since the atomic number of the element is 29, the atom is copper. The complete symbol for the atom may be represented as shown here. In some cases, atoms of the same element may have the same number of protons, that is, the atomic number, but may have different numbers of neutrons. In other words, the atoms have the same atomic number but different mass numbers. Such atoms are called isotopes. Isotopes of the same element occupy the same place in the periodic table because they have the same atomic number. Let us look at a few examples of isotopes. 99.985% of hydrogen atoms contain only a single proton in their nucleus. This isotope of hydrogen is called protium, 1H1. Remaining 0.015% contain two other isotopes, deuterium, which contains one proton and one neutron, and tritium, which contains one proton and two neutrons. You can see that all these three isotopes have the atomic number 1 and mass number 1, 2, and 3 respectively. Carbon has three isotopes with mass numbers 12, 13, and 14 respectively. Similarly, chlorine, atomic number 17, has two isotopes with mass numbers 35 and 37. Isotopes of the elements other than hydrogen do not have special names. They are represented by simply indicating the mass number on the element's symbol. The chemical properties of an element depend on the number of electrons present and their configuration within an atom, and not on the number of neutrons. Hence, as the isotopes have the same number of electrons, they exhibit similar chemical properties. However, as the mass of isotopes differ due to the different numbers of neutrons present in an atom, their physical properties differ from each other. Some atoms of different elements are found to have the same mass number but different atomic numbers. For example, 18Ar40, 19K40, and 20Ca40 have same mass numbers but different atomic numbers. Such atoms of different elements having different atomic numbers but the same mass numbers are called isobars. Isobars have different chemical properties because they have different atomic numbers. the year 1896, French physicist A.H. Becquerel discovered some new radiations emitted spontaneously by crystals of potassium uranyl sulfate, K2UO2SO42. On further investigation, he found that these rays were emitted by the element uranium. It was experimentally found that uranium emitted these radiations irrespective of its state of chemical combination, and physical conditions such as temperature, pressure, etc. It showed that the phenomenon involved was related to its nucleus. Some more experimental observations were that these radiations have more penetrating power than X-rays, and they get deflected in the presence of an electric field and a magnetic field. These new radiations were named Becquerel rays. Subsequently, Marie Curie, along with her husband Pierre Curie, found two more elements, polonium and radium, that emitted similar radiations. The term radioactivity, which refers to the phenomenon of emission of all such radiations, was coined by Marie Curie. The phenomenon of radioactivity is defined as the spontaneous emission of highly penetrating radiations by some unstable nuclei. Since these emissions are spontaneous, we call the phenomenon natural radioactivity. Elements that give high energy radiations spontaneously are called radioactive elements. Some radioactive elements are uranium, thorium, polonium, and radium. Rutherford conducted many experiments to study the nature of the radioactive rays emitted by radioactive substances. He kept some radioactive substance inside a narrow cavity drilled into a thick lead block. The radiations emitted by the radioactive substance emerged through the cavity. A photographic plate was positioned above the cavity, and the radiations were made to pass through a strong electric field, as shown here. The radiations were allowed to fall on the photographic plate for few seconds. When the photographic plate was developed, three distinct spots were observed. Let us call them A, B, and C. Spot A is very dark and appeared on the negative side of the photographic plate. The angle of deflection of these radiations was very small. Rutherford concluded that the radiation responsible for the formation of spot A must consist of positively charged heavy particles. These radiations were named alpha radiations, and the particles were called alpha particles. Now look at spot C. It is moderately dark and appears on the positive side of the photographic plate. The angle of deflection of these radiations is large. Rutherford concluded that the radiations affecting the photographic plate at spot C must be negatively charged lighter particles. These rays were named beta rays, and the particles were called beta particles. Rutherford also concluded that spot B, formed in the middle of the plate, must be due to radiations that are not affected by the presence of the electric field. He named them gamma radiations. Further studies showed that alpha particles are the nuclei of helium. Beta particles are electrons, and gamma rays are high-energy electromagnetic waves. Let us now study the properties of alpha, beta, and gamma radiations. Let us first study the nature of these radiations. Alpha particles are doubly ionized helium atoms, or simply the nuclei of helium. The mass of alpha particles is approximately 4 times the mass of a proton, and the charges is 2 times that of a proton. Beta particles are electrons that originate from the nucleus. Their mass and charge are equal to the mass and charge of an electron. Gamma rays are electromagnetic radiations of short wavelength. The speed of alpha particles ranges from 10 to the power of 6 to 10 to the power of 7 meters per second. The speed of beta particles is of the order of 10 to the power of 8 meters per second. Gamma rays travel at the speed of light. Alpha particles very strongly ionize the gas through which they pass. The ionizing power of alpha particles is 10,000 times stronger than that of gamma rays. The ionization power of beta particles is less than that of alpha particles, and more than that of gamma particles. The ionizing power of gamma particles is very low compared to that of alpha particles and beta particles. The penetrating power of alpha particles is small compared to beta particles and gamma particles. The penetrating power of gamma rays is very high. The penetrating power of beta particles is more than that of alpha particles and less than that of gamma rays. In the presence of an electric field, alpha particles are deflected towards the negative electrode and beta particles towards the positive electrode. Gamma rays do not get deflected in the presence of either an electrical or a magnetic field. Both alpha and beta particles deflect in the presence of a magnetic field. All these radiations can produce fluorescence when incident on material like zinc sulfide. These radiations are harmful and can cause radiation damage. That atoms of the same element with the same atomic number but different mass numbers are called isotopes of the element. For example, carbon has 3 naturally occurring isotopes known as carbon-12, carbon-13 and carbon-14. Carbon-12 and carbon-13 are stable, but carbon-14 is unstable and exhibits radioactivity. Isotopes that exhibit radioactivity are called radioisotopes. These radioactive isotopes continuously emit alpha, beta or gamma particles to attain stability. All elements with atomic number greater than 83 exhibit radioactivity naturally and are known as naturally occurring radioactive isotopes. Radioactive isotopes of smaller atomic numbers can be produced artificially by artificial transmutation. In this process, a stable nucleus is bombarded with high-energy particles like protons, neutrons, or alpha particles. The new nucleus so formed is unstable and exhibits radioactivity. For example, when a high-energy neutron collides with the nucleus of nitrogen, carbon-14 is formed. Carbon-14 is unstable and exhibits radioactivity. It emits beta particles and converts back to nitrogen to acquire stability. Radioactive isotopes find many applications in different fields, including medicine, agriculture, and industry, and in carbon dating. Let us first learn about the uses of radioactive isotopes in medicine. In medicine, radioactive isotopes are used for diagnosis as well as for therapeutic purposes. In many of these applications, the radioisotope concerned is introduced into the body. When used for diagnosis, the course of the radioisotope through different stages of metabolism is studied. This study often helps in determining the existence of disease, its location and character. For example, the functioning of the thyroid gland can be studied by observing a small dose of radioiodine, I-131, given to the patient. A radioisotope of iodine is used in the therapy of hypothyroidism. Similarly, radioiron is used in the investigation and therapy of diseases related to the bone marrow. Radiocalcium is used in the diagnosis and treatment of bone cancer. Radioisotopes of sodium and phosphorus, sodium-24 and phosphorus-32, are very useful in diseases related to the heart and kidneys. High-energy radiation can destroy human cells. In fact, malignant cells are more sensitive to radiation than normal cells. Radiation from cobalt-60 is used in the treatment of cancer to kill cancer cells. Let us now study the applications of radioisotopes in industry. Radioisotopes are used to study the wear and tear of various internal parts of a machine. This is also used to develop a suitable lubricant to prevent wear and tear. Radiocobalt is used to detect the internal flaws in a cast material. In some applications, radioisotopes are used to dispel static electricity acquired by some materials. Radioisotopes find several applications in agriculture too. Unnecessary mutations of plants can be prevented by irradiation or gamma radiation of seeds. This improves the yield. A fertilizer suitable for a particular soil is chosen after determining the phosphorus content of the soil using radiophosphorus. To study the uptake of phosphorus by plants, the isotope P32 is used. To study the transport of minerals in plants, sulfur-34 is used. Perishable goods like cereals are kept fresh beyond their normal life by exposing them to mild gamma radiation. The gamma radiation destroys bacteria. Another important application of radioisotopes is found in carbon dating, where the radioactive carbon-14 isotope is used. Carbon dating is a technique developed to determine the approximate age of ancient biological material. Cosmic rays entering the Earth's atmosphere knock neutrons out of atomic nuclei in the upper atmosphere. These fast-moving neutrons hit ordinary nitrogen 14N at lower altitudes and convert it into 14C. Ordinary carbon C12 as well as the radioactive carbon 14 combine with oxygen to form carbon dioxide. In photosynthesis, carbon dioxide is absorbed by plants, and they, in turn, are eaten by animals. So, a leaf or a tree or even a bone contains both the isotopes of carbon. Because C14 is so well mixed up with C12, the ratio of carbon 14 to carbon 12 is the same in a sample of a leaf from a tree or a part of an animal's body. Radioactive carbon 14 atoms constantly change back to nitrogen 14 atoms. In living things, the ratio remains the same because the decayed carbon 14 is replaced by the food they take. However, as soon as a plant or animal dies, the C14 atoms that decay are no longer replaced. So, the amount of C14 in that once living thing decreases as time passes. In other words, the carbon 14 to carbon 12 ratio gets smaller. By measuring the percentage of carbon 14 in biological remains, the length of time for which the specimen has been dead can be estimated. In an atom, electrons revolve around the nucleus. The electrons in the inner orbits are strongly attracted by the nucleus, and hence they are called bound electrons. However, the attractive force of the nucleus on the electrons revolving in the outermost orbit is weak. In metals, the outermost electrons are not bound to a particular atom. Though they are within the boundaries of the metal, these electrons are free to move throughout the body. These are called free electrons or conduction electrons. Can these free electrons come out of the metal surface? If an electron leaves the surface, the metallic body becomes positively charged and attracts the electron back to the surface. In order to escape from the metal surface, an electron needs sufficient kinetic energy. If the kinetic energy is less, the electron is attracted back to the metal surface. Here, we see that with a little more kinetic energy, the electron moves farther away, but is still attracted back to the metal surface. The electron is able to escape from the metal surface only when it has kinetic energy sufficient to overcome the electrostatic attractive force. The energy required by the electron can be provided in different ways. When a metal surface is heated, the electrons escape from the surface of the metal. This phenomenon is known as thermionic emission, and the electrons thus emitted are called thermions. If the electrons are emitted by a metal surface after absorbing light energy, then the phenomenon is called the photoelectric effect. and the electrons thus emitted are called photoelectrons. Let's now see what the minimum energy required to emit an electron is. Different elements require different energies to emit an electron. The minimum amount of heat energy required to emit an electron from a metallic surface is called threshold energy or work function. Usually, work function is expressed in electron volt eV. For example, the work function of tungsten is 4.52 electron volt and 1 eV is equal to 1.6 into 10 raised to the power minus 19 joules. Let's see the work functions of some common elements. The work function of silver is 4.7 electron volts. Chromium is 4.5. Gold 5.3. Copper 4.8. Zinc 3.8. Calcium 2.87. Barium 2.6. And magnesium 3.7. Let's now see an important discovery that was made before electrons were discovered. Most of you must know that the electric bulb was invented by Thomas Alva Edison. Thermionic emission was first observed by Thomas Alva Edison while trying to find the reason for the breakage of filaments and uneven blackening of his incandescent bulbs. His observation of the emission of charged ions from a red-hot filament came to be known as the Edison effect. To understand these charged ions better, Edison placed a metallic plate in his bulb and connected it externally to a battery through a galvanometer. The filament gets heated when current is allowed to pass through it. He observed a deflection in the galvanometer when the metallic plate was connected to the positive terminal of the battery. And no deflection when it was connected to the negative end of the battery. The charged ions emitted from the red-hot filament of the bulb were actually electrons, which were subsequently discovered by J.J. Thomson. This fact of the emission of electrons from a heated filament is used in many applications of electronics, like the valve diode and the cathode ray tube. A valve diode is an electronic device that conducts electric current in only one direction. J.A. Fleming developed the first thermionic diode that works on the basis of thermionic emission. Let's see how a valve diode works. A low-tension battery, A, is connected to the two ends of a filament. When current is passed, the filament gets heated and thermions are emitted. A small region around the cathode with excess free thermions is called space charge. When a metallic plate is connected to the positive terminal of a high-tension battery, it behaves like an anode and attracts electrons, or thermions, from the cathode, and current starts flowing between the two electrodes. This current is unidirectional and can be controlled by varying the voltage of the high-tension battery. In thermionic emission, the measure of the number of thermions emitted per second is very important and is called the rate of thermionic emission. The following factors influence the rate of thermionic emission. It depends on the nature of the metal surface. It It is inversely proportional to the work function of the metal used. The rate of thermionic emission is directly proportional to the temperature of the surface. It is also directly proportional to the area of the surface. The material that is used as a thermionic emitter must have a low work function and a high melting point. Let's now see some of the most useful thermionic emitters. Tungsten. It has a high melting point of 3660 Kelvin and starts emitting thermions at 2500 Kelvin. It has a high work function of 4.52 electron volt. Thoriated tungsten. Tungsten is coated with thorium and carbon. This starts emitting electrons from 2000 Kelvin and its work function is 2.6 electron volt